Hello everyone, welcome to my YouTube channel. Today I'm solving Leetcode question 329, longest increasing path in a matrix. Given an m times n integers matrix, return the length of the longest increasing path in matrix. For each cell, you can either move in 4 directions, left, right, up, or down. You may not move diagonally or move outside the boundary. For example, wrap around is not allowed. So what does that mean? So you cannot just move out of the boundary and move back. That's not allowed. So let's take a look at example 1. So the longest increasing path is indicated by 1, 2, 6, 9. So the length is 4. That's why the output is 4. And then for the example 2, the longest increasing path is 3, 4, 5, 6. The length is still 4 here. In the example 3, there is only one element in the matrix. So the longest increasing path is just itself equals 1. So how to solve this problem? So when we look at the problem and we find out 4 directions, left, right, up, or down, we may think about, okay, that's very similar to the DFS problem we solved about the number of islands and then a different variation of that. But then the thing is, we need to keep track of, okay, so what is the longest path? So first, let's take a look at one cell. So starting from here, so let's say starting from 6. So what is the longest path? So we check longest increasing path. So basically we check the going up, so that's 6, 9, 2, because it cannot move any further beyond 9. It can go to 6, 8, but it can not move any further, goes beyond 8, because all numbers adjacent to 8 are actually smaller than 8. So we check the neighbors in 4 directions. We do not check neighbors diagonally. So from 6, it cannot move left because this number is equal to 6, and then it cannot move down either because 1 is less than 6. So basically, the idea is, okay, starting from cell, you can check 4 directions. Move up, left, and right. And then if we know, okay, so if the length, let's just check, okay, so what is the length of that in the 4 directions, and then you just take the maximum path. So we are doing that for every cell on the board. So in that case, so it seems like a DFS problem. So however, the runtime will explode if we just doing it this way. Let's take a look at one scenario. Let's think about, okay, so here, when we consider this cell, so we check the adjacent cell, and then from here, we also check, compare this 9 with 4. So that's kind of the comparison checking we are doing. However, when you look at, let's say, starting from 1, and then 1 goes to 6, and 6 goes to 9, and then this 9 you also compare with 4. So what do you see here? The repeated calculation. So okay, so then in this way, it hints us that we need to utilize some data structure to actually store or cache the already encountered value so that we do not need to repeatedly calculate them over and over again. So in that case, so it's actually a dynamic programming problem. We're going to utilize a 2D matrix to keep track of the longest increasing path from each position. So okay, let's after that, let's start coding. So the idea for solving it is just dynamic programming. So cool, let's first get the dimensions of the matrix. I'm having another data structure, another matrix to keep track of, let's say, the longest path for all the numbers encountered, so that I don't need to repeatedly calculate that. So in that case, why initialize it? Let me initialize it to so cool. Let's first try to initialize it to 0. Okay. And then start our Dfs traversal. So remember what we need from the Dfs traversal. So we need to input the index we are currently visiting. And then remember, there's a comparison here. So we check the longest increasing path. So we always compare this ij with previously encountered numbers on the path. Let's say, okay, starting from 4, we are moving left. So now we are at position 0, 1. That's the index for this 9 in the middle. And then we are visiting it. So since we come from the path from 4, instead of other directions, so our previous number is 4 along this path. So we must compare this number with the previous number. So that's why we also input the previous number. So let's say if my I is less than 0, or I is greater than or equal to m, or j is less than 0, or j is greater than equal to n. So it's outside the boundary. So in that case, I just return 0. And then from here, let me do the comparison. Or if matrix I, j is less than or equal to the previous, we just return 0. So you may ask why. So because let's say if we are moving, so the previous one, let's say previous one is 4, and then the next one is actually 9. So in this case, it satisfies our condition. But what if the previous one is let's say the previous number is 10 or something like that? So in that case, we just return 0. And then we check the up. Up equals dfs. We're going up. I minus 1 j. This previous number is I matrix I j. We're going down. dfs I plus 1 j matrix I j. We're going left equals dfs I j minus 1 matrix I j. Right equals dfs I j plus 1 matrix I j. Okay, so after checking it for directional, basically we get the longest path in all the 4 directions. So in that case, we want to return maximum from the up, down, left, right, plus, plus the current number, right? So we also have additional lengths, like at the position ij, so plus 1. Cool. So we have coded our DFF solution. However, we haven't utilized our the cache we initialized, the DP matrix, to store the values we have already encountered, to avoid repeatedly calculating like the same value over and over again for different paths. So in that case, let's try to add that piece. So at the very beginning, if our ij, let's say previous, is already in, okay, so if my dp I j is greater than 0, in that case, it means we already replace it with a number. Remember, we initialize this one to minus 1. So in this case, it means we already do the calculation if this value is greater than 0, because remember, the minimum value is 1. The minimum longest increasing path is 1. Let's say from any number. So let's say we cannot go in any of the directions. So the longest increasing path is just itself. So the minimum value is 1. So that's obviously greater than -1. So we can use this condition to denote that we have already calculated the value at position ij. So in that case, we just return dpij. Otherwise, after we do the calculation, we assign dpij equals the maximum value, and then return dpij. So that's kind of how we implement utilizing another matrix to store the value we have already calculated. So now let's just call it. So basically check for every position. Let's get a max path, max length, long max length equals 0. Initialize it to 0. For I in range M, for J in range N. Let's try to run this one. So basically, it's DFS IJ. Check each position as the starting position, and then initialize our previous value to -1. So in that case, our starting, let's say we're starting from position ij, so the matrix ij is always greater than -1, our initial value. So in this case, we get just like good starting value. So the length, so maximum length equals the max between itself and then the value returned. After that, we just return the maximum length. So let's try run the code. List the index out of boundary. So I need to first check if it's within the boundary or not. So here. Okay, I still got the list index out of range arrow. Okay, so I know I made a mistake in initialize this DP matrix. So it has n columns and m rows, but somehow when I initialize it, I reverse it. So that's why it calls the list index out of range arrow. Okay, so this is our solution. So let's try walk through this solution one more time. So cool. So in this problem, it specifies that from each cell you can move in 4 directions: left, right, up, or down. So 4 possible movement from any cell. And then we know that we calculate the longest increasing path in a matrix, that we do not want to repeatedly calculate the values that we have already encountered before. Let's say going down from, let's say we were trying to check compare 9 and 4. When we look at this path, we could consider that. We could do the comparison, and then we check on 6, 9, and then from here, we can also do the comparison. So we do not want to repeatedly calculate the value over and over again. So that's why it's a dynamic programming problem. And we utilize another matrix, we call it dp, to actually cache the value we have already calculated. And then in this function, we call it dfs. We keep track of the cell we are visiting. So we are going to visit the cell ij when we call the dfs ij. So when we call dfs ij, we are visiting cell ij, and ij is just the starting point from here. And then we get the previous value. Remember, so when we get into a position, let's say get into 4, we can enter 4 from the cell below it or from the cell to the left of it, because from each cell we can move in 4 directions. So that's why we want to also track the previous value so that we can know if this path is the longest increasing path or not. And then we compare the value to see if it's out of the range. So those indicates, okay, I less than 0, I greater than or equal to m, or j less than 0, or z greater than or equal to n, indicates that, okay, index out the boundary. What if the index is not of the boundary? Then we compare the current value with the previous value. So remember, we want the longest increasing path. So if my current value is less than or equal to the previous value on the path, it indicates that, okay, this path does not satisfy the requirement longest increasing. So in that case, we just return 0. So why return 0? Remember, later, when we traverse into 4 different directions, we just take the maximum among the 4 directions and then plus 1. 1 means the current value. So this 0 means that, okay, the longest increasing path when you start with the traversing down or moving from the current cell, not including the cell itself. So that's why we return 0. And then because we already encountered the length of itself later, utilizing this plus 1 here. Okay, so we handle these edge cases. Okay, so now we kind of get us, after we handle those edge cases, we kind of have a path that's satisfying the requirement. So in that case, we check, okay, if this ij at this position, the longest increasing path has already been calculated. So in that case, if it's greater than 0, then we know that we replaced with the number we already calculated, since we initialize this dp cache into with a value of -1. So in that case, if it's already calculated, there is no need to start a traversal and then repeatedly calculating it. We just return the value itself. If it's not calculated, so let's see, we can move in 4 directions. So if we move up, the next cell is going to be I-1, j. So that's the coordinates for the next cell. And then the previous value for the next cell is this current, is the value at the current position ij. So that's what we pass into the dfs function. If we going down, so then we got the index I plus 1j, and we can go left and we can go right. Basically, dpij represent the longest increasing path starting from the position ij. So in that case, we checked, okay, from ij, all the 4 directions we can go. So it's max, and then we pick the maximum. And then we also need to consider itself. So add itself to it. So that's why we do +1. And then in that case, we just return the value, the longest increasing path starting from position ij. And then we initialize the variable called maximum length, utilized to track of the maximum length of all all increasing paths in the matrix, because we want the longest one. And then we loop through every cell in the matrix, and then we kind of calculate the longest, the increasing path, the length of increasing path starting from cell ij. And here we assign -1 as the previous value, So because no matter what the value it is in the matrix ij, it's always greater than -1, so it's satisfied as the constraint. And then we just keep comparing the result with the existing maximum length, the maximum length we already calculated. If it's greater than that, we just update that. So in the end, we just return the maximum length. So yeah, that's the overall solution. If you like my video, please don't forget to subscribe to my YouTube channel. Thank you.